2.7, this is parent functions and transformations, okay? We're going to start off with parent functions. I think you've done some of this stuff before. I hope that the way that I explain it feels a little more useful to you. And we'll see, okay? So all of these parent functions that I'm going to show you on page 301. So there's 4 of them on page 301 if you want to screenshot that rather than trying to take pictures of the board. I'm gonna put one of the parent functions up at a time and explain each one. But go ahead and screenshot page 301 and you can crop in those parent functions into your notes. That'll probably be easier than trying to take pictures of the screen. So go ahead and do that now. You might also leave some space, you know, and crop it in different ways like I did here, because you're going to want to write some notes because, for example, all of this information below each graph is very mathy, and you might want to translate it for yourself. So as you're inserting those pictures into your notes, you might give yourself some room, kind of like I have this here, so that maybe you can write next to it and rewrite this in terms that maybe are more understandable for you. If you get what's written down here, then that's great and you don't need to worry about it. But I think sometimes translating it into sort of teenage words is more helpful for you, and therefore will be more helpful as you're studying and preparing for exams. Let's talk about this first one. Constant function. Basically what a constant is just a regular number. It's called a constant because it never changes versus a variable that varies. Okay? So any sort of number that you can think of, any real number, that's a constant. As we've discussed earlier, whenever I have y equals some constant where there's not an x, it's just a horizontal line. Okay? And that's all that this is saying. Y equals a number, where a is any number. The domain's all real numbers, the range is all real numbers. Anytime you have a horizontal line, you have something like this. Okay? Whatever the value of this number is here, in this case it's 1, that's where the line will go on the y. So y equals 1 in this case. If y was 7, we'd be up here somewhere. That's the constant function. And keep in mind what parent functions really are. Parent functions are kind of the starting point for all other graphs. All right, it's like the most basic model graph that exists. Okay? No upgrades, no fancy colors, you know, nothing like that. The most basic model that exists of that particular one. Okay? Constant functions are all pretty much the same. All right. The second one that you see is what's called the identity function. Okay, and in this case it's y equals x. Identity function, okay, is when y equals x. It's the identity because it's the same. Right? We will change and move away from the identity function in different transformations. That's why this section is all kind of together. Okay. But just know that every y and every x are equal to each other. So all my points, so here are the points. They write them as AA, but like for example, my points would be 1, 1, 2, 2, 3, 3, 4, 4, negative 4, negative 4, negative 8, negative 8. They're just the same. Same thing, domain and range are both all real. Questions on either of those? Next 2. Absolute value function. We already talked about this. Okay, we talked about this in 2.6. The shape is going to be a V. Right. The domain is going to be all real numbers. The range, and this, again, this is the, like I said, the most basic model, the parent function. The range is y greater than or equal to 0. Obviously, you worked with some functions yesterday that the range changed because the graph moved. All right. But everything starts from this place. And then the last parent function that we're going to look at are quadratics, which are parabolas. Okay, y equals x squared is, again, the most basic model of a quadratic. The domain and range work the same for absolute value and quadratics. There's a minimum value here, so the range is y greater than or equal to 0. X, the range is all those real numbers. Now, every function that we've ever really worked with comes in some variety or form of one of those 4 functions. Whether it's a constant function, identity function, an absolute value function, or a quadratic function. What changes could be the size of that graph, could be the position of that graph, could be the direction of that graph. And when the direction changes, or the size changes, or the position changes, what we call that is a transformation. Okay? So if I take a parent function and transform it, it's still going to be an absolute value function, if that's what we started with. Or it's still going to be a straight line, a linear function, if that's what we started with. Or it's still going to be a parabola, if that's what we started with. Okay? We can change the size, shape, and position, which is the next part of transformations. So we start off with this sort of basic model, and then we're going to upgrade it. We're going to change it, we're going to move it. And we can change it or move it in different ways. Okay, and the first way that we're going to talk about is what's called a translation. A translation is when you take the graph and you slide it. You reposition it. So it can be moved left, right, up, down, or any combination of those. Or one of each. Obviously you can't move left and right. It either moves left or right, and it can also move up or down. Translations are also known as slides, because the graph actually slides. So we use those words interchangeably. If we say a translation, we mean a slide. If we say a slide, we mean a translation. Okay? Again, we're just talking about repositioning. We're not talking about flipping. We're not talking about changing size. We're talking about where it's located. That's it. So all of those four parent functions always kind of center around the origin, except for the constant function. A translation won't. It'll move on us. Okay? So, when I have a vertical, in case you didn't know what vertical meant, up or down. If I have a vertical slide, it occurs when a constant is added or subtracted outside of an x term. And I'm using this, I might as well have written it like this, outside with like quotation marks. I think it's easier to understand what that means with examples. And I'm going to show you some examples of what equations look like with vertical slides. I'm going to show you some examples with equations that have horizontal slides. I want you to pay close attention because in your mind, you have to sort of mitigate all that stuff. I use the word outside. Maybe outside's not the right word for you. If it works for you, then great. I'm glad I helped. But if there's another word that makes more sense or another descriptor that makes more sense to you, then I want you to use that. All right? So here's some examples. Okay, there are 3 different examples of vertical slides, vertical translations. Go ahead and write those down, and then we will talk about what those actual changes are. Let's look at this first one. So here's what I mean by outside. Particularly, it's really easy to tell with the absolute value. Clearly, this minus 3 is outside of the x. I have this absolute value that sort of serves as a barrier. In this case, this 7 is outside of the x squared because the 7 is not also being squared. Just the x is being squared. With the identity one, it's always going to sort of look the same. These are all vertical slides, and these values 7, negative 3, and 9 are outside of the x term. Hopefully that kind of makes sense to you. So, anybody want to take a guess in which direction the parent function would slide for this first one? Mateo, what do you got? Up how many? Up 7. Correct. Okay. What the key is with understanding translations or transformations is that you can just take the parent function and based on what kind of numbers are being added, subtracted, multiplied, understand, the goal is to understand how the parent function will be sort of upgraded from the basic model. I keep using that phrase, I'm going to keep using it. Okay? All right, for g of x, Andres, what's going to happen, you think? Down 3. How many agree with him? Okay. And the last one, what do we think? It's all together. Up 9. So that's the vertical slide. The changes to x happen outside of it. Okay? Questions? Let's look at horizontal slides. Now there's something highlighted here in red because it's pretty important. And after you write that down, I'll talk about it a little more. So the horizontal slide, left to right, occurs when a constant is added or subtracted inside of an x term. Okay? And that really only happens in two of the cases. It happens with the absolute value. It happens with the quadratic. All right? The key thing here is the horizontal slide, it actually moves in the opposite direction of the sign. So on the vertical slides, when it was plus 7, that first example, it went up 7. With the horizontal slide, it will actually move in the opposite direction. So you have to be careful of that. And that happens as we work through functions and we work through solving functions later on this year. You're going to watch that that sign's going to change on you when it's inside the parentheses or inside the absolute value. So just be careful on that when we're talking about the x change. So here's examples, okay, that I want to show you. So notice again, the adding or subtracting is now happening. This is when I say inside. It's going to be literally inside a parenthesis, or it's going to be inside an absolute value, or even in the problems that we were working on yesterday, inside the greatest integer function. Okay, so there will literally be some type of grouping symbol inside a radical. Okay, there will be some type of grouping symbol, and the adding or subtracting of the constant will occur inside of that grouping symbol. So in terms of being able to recognize if it's a vertical or horizontal change, that's your key, inside or outside. That's kind of why I use those terms. All right. Questions on that distinction? Raise your hand if you sort of get what I'm saying by the inside and outside. That's what I'm really trying to make sure you're good on. If you're not good on that, let me know. We'll figure it out. Okay. So in this case, since both of these are inside, I've got a minus 5. Which direction is this going to slide as a parent function? Nick? Right, how many? 5. Okay, so key here, opposite direction. Even though your instinct might want to say left 5 because it's negative, with horizontal slides you've got to use the opposite direction. So this will actually go right 5. So go ahead and just write in on your notes what the second one is, and we'll see if you're right. All right, Isabella, what do you got for me? Which way is this going? Left 2, okay. How many agree with Isabella? Good, because she's right. Left 2. So again, opposite sign when it's on the inside, and then the constant tells you the number of units that it moves. So that's translations. Up, down, left, right. The size and the shape of the graph aren't changing. The position with respect to the origin does change. Okay? Questions? All right, let's look at this transformation. A reflection is a flip. Those are the ones we're going to talk about today. We're going to only talk about two kinds of flips today. It either is going to flip over the x-axis. So the mirror is the x-axis and the reflection goes on the other side of the x-axis. Or it's going to reflect about or over the y-axis. Okay? And that's what that says. It's either going to flip over the x, or it's going to flip over the y. For now, those are the ones we're going to talk about. You can do reflections that flip over other lines besides those two axes, but we're going to just focus on those for this section. So, if the negative is outside of the x, again, I'm still using that whole inside-outside thing. Negative this time is going to be in front of the x. If it's outside of the x, then it flips over the x-axis. When there's a reflection, you're looking for a negative sign. That negative sign in front of a parent function indicates to you there's a flip. When you worked in your homework yesterday on the last absolute value function, that the v went upside down, if you looked back at that problem, you'd notice that there was a negative number out in front of the absolute value sign. Okay? So that's why it flipped over the x. So here are a couple examples. Now, I'm going to talk about this one and make sure we are clear on what's going on in this one. But go ahead and write that down first. Obviously, I have the negative outside the absolute value. There's no issue there. We tend to have a problem with this. Many of you look at this and you think it's that the x is negative and then it is also squared. You run into an issue with this problem when you try to plug things like this into the calculator. I want you to understand what this really means. This really means an equation like, and I'm putting a big space in there on purpose. It's like, look, the x is squared, and then it's like you drop the negative on it. So it's the opposite of x squared. The negative is not being squared. Okay? This is order of operations. Think of this as a -1. You do the power first, and then the multiplying, if that's how you want to think about it. Okay? So this is how you need to think about this problem. And this is where the negative is outside, like it's far away. It doesn't really want to be there, kind of thing. Okay? Then, of course, if the negative's on the inside, it flips over the y. And then take those examples and change them up. So now the negative is being squared here because it's in the parentheses. Again, that inside-outside idea. I don't need to put parentheses here because order of operations tells me the x is the only thing being squared. Down here, I put the parentheses to ensure that that negative is also being squared. That's reflections. So we've looked at repositioning the parent function, sliding it. We've looked at flipping it. Now we're going to look at changing its size. Okay. The shape itself will still be the same. Absolute value function will always be a v. It just might be a wider v or a skinnier v. A quadratic function will always be a parabola. Same thing. It might just be a wider or a skinnier sort of v. And that's the last type of transformation we look at. It's called a dilation. Dilation is when a parent function is stretched or compressed. We'll talk about the definitions of those words here in a second. Here's a kind of example I want you to think about. All right, every single one of you at some point recently, in fact today, have inserted an image into a file, into a document. Okay, you've changed the size of it to fit how you need it to fit. Right? You'll grab a corner and pull it out and enlarge the whole thing, so that the shape will remain the same, but the size of it will get bigger. Or you'll grab a corner and slide it in to shrink it down. Or you can grab a side and pull it up and stretch it out, or pull it down and compress it. That's what compress means, sort of squeeze it down. Okay? That's the same idea with dilations. You're just pulling a horizontal or vertical side to change the shape and size of the parent function. Now, I'm going to give you a couple rules. Certain numbers you look for will tell you that it's going to be stretched. If you have other numbers, it will compress it. And I'm going to give just some examples, okay? And I actually went into the graphing calculator and I pulled in some pictures, so you'll see that in a minute. So if you want to take pictures of those while we're taking notes here, you're welcome to do that. I will tell you that there's going to be 2 graphs per slide, so even though I'm going to only show you one at a time, you might wait to take a picture after the second graph comes up, okay? First of all, the rule. When you multiply x by a number greater than 1, the graph is stretched vertically. So that's like grabbing the top part of the rectangle of your image and pulling it up. Stretching it almost looks like the graph will get skinnier when you stretch it out. It's a horizontal change. It's a vertical change, not a horizontal change. It's a vertical stretch. Now, the first graph that I'm going to put up here, like I said, wait till I put the second graph up to take a picture of it. The first graph, or for that matter, you can use your graphing calculator and plug it in yourself. The first graph will be the parent function. And I used a parabola. I used y equals x squared as an example. You could do the same thing with the absolute value. Or for that matter, you could do it with the identity one. Here's my first graph, okay? That's y equals x squared. That's the parent function, okay? Now, I think I chose 5x. I think I multiplied it by 5 on the next one. And so that's what happens. Yeah, 5x. So it's the same exact window. Notice the settings. It goes from -10 to 10. It goes up to 15. So it's like I took the top of the image right here. I like grabbed, if this was an image, and I grabbed it and I pulled it up. Like you've done in a document with images a million times. And so it took the graph itself and stretched it up. So when I get a number being multiplied by x greater than 1, it will stretch it. Vertical stretch. Now, the next picture, if you want to insert it, you can. You don't have to. I basically put these two different graphs on the same grid. So just know that when I switch over here in a second, all you're doing is seeing a comparison of those two combined together. Okay. So again, it's like taking the red graph and stretching it vertically to get the blue graph. The bigger the number that you multiply by, the sort of skinnier the graph will be. You're stretching it out further. The smaller the number is, the closer to the red graph we will have. Okay? Questions on that? Now, in this case, we're talking about a number greater than 1. So, what we're going to look at next is a number less than 1, but there's a restriction. And so here we go. The restriction is greater than 0, but less than 1. Because once we go less than 0, it's the negative numbers, and now we're talking about a flip as well. So remember that negative in front is a reflection, or a flip. So we're specific about greater than 0. Because then we start combining flips and dilations. So that's why you see the restriction is greater than 0, but less than 1. Graph is compressed vertically. So instead of this time taking the top of the image and pulling it up, we're going to actually take the top of the image and smush it down. Okay. So again, same thing. The first graph is the parent function. That's why I only put 2 up there. Okay. I used 1/4 here, which is greater than 0 and less than 1. And notice how it kind of gets smushed down and gets wider, and that's what compressed means. And the next image you're going to see is with them combined together in one grid. So again, here's the thing. You've all had an image in a document that you've inserted and you've altered in some way. If you grab the top of the image and pull it up, it will stretch it vertically and make it look skinnier. If you grab the top of the image and smush it and pull it down, it'll sort of flatten it out or smush it down a little bit or compress it. Okay, you've all done that before. All right, and that's what they look like combined together in one grid. Okay, so basically taking the red graph, smushing it down until it looks like the blue graph. Obviously, if you change the value that x is being multiplied by, it will impact how much smushing goes on. Okay? Are there any questions? So you're going to do lots of different things in your homework tonight. Okay? One of the things that you're going to do is it's going to ask, what's the change? How does the parent graph change based off the new equation? And so you're going to say things like up, right, down, and how many like we did. Or you're going to say it gets stretched or compressed. Or you're going to say it flips over the x-axis. Things like that. And then you're going to graph it. So I want you to do 2 things when you graph it. I want you to, 1, make a table of values. Graph it by hand, and then I want you to use your graphing calculator to verify that what you did is correct. Okay? And that's kind of all you have to do. You're using all these different types of transformations to identify those, and we should be at a place now when you see a quadratic, you see something to the second power, you know the graph's a parabola. When you see an absolute value, you know it's some type of v. When x is to the first power, it's linear. When there's no X at all, it's horizontal. Those kinds of things, we should be at a place where you should be able to just recognize those. Boom, boom, boom. Okay?